Hello fellow problem solvers. So today I'm doing a problem from the Italian Math Olympiad 2015, problem number 6. This is a good problem to try out if you've just done some technique combinatorics and you want to try to solve an actual combinatorics problem where you don't know what technique it is. Great problem to do then. And it's very playful in its nature. And if you wanted to do it all by yourself, a minimum of 25, ideally 45 to an hour, not more than 2.5 hours, is the time I would suggest you try it out. If you'd like to go along with us, read it and think, what is the problem about for the next 5 minutes? And now let's begin. So we have this game that these two people are playing, and it starts off with some integer, and then you can either write down one divisor of that integer, or you can add 1 to the integer. But if you write a divisor, your number of points increases by 1. If you add 1, it decreases by 1. Okay, now, and you want to see, you don't want to get to 0. You want the other person to get to 0 before you. Okay, so this seems very difficult. Like usually in games, it's like if you reach some number, it's done. But here it's like you have points, 2 moves that you can make. So it's a bit different. So what do we do when we see something different we've never seen before? The answer is play around, and which is what I suggest you do for the next 10 minutes. And now here's some playing around. And the first sort of playing around is to start off with these smaller numbers. And we see, okay, if we start with 2, we are forced, like if we have a prime number, we're forced to go to p plus 1 due to the second thing, which means we're forced to make move 2 and lose a point. Now, let's just like look at this initial thing. What do we have? If we're like the first player, if we're playing on 2, like this is A, and then the second player is on 3, they're forced to do a -1 as well. Then we're both -1, so in some we're not anywhere, like we're not different. And then we're here, and if I add a 1, I put the second player, I put C in charge, I put Charles in charge again. And then Charles can go here or could go to 5. So let's see what happens when he goes to 5, because here I'm just like putting Charles in charge. So let's see what happens here. Okay, now say I played -1, now I have -2 as A. Charles has -1, so Charles is again forced. I want to look at forcing moves more so than moves which control like moves which control the other player are good for us, because that gives us predictability. It helps us decide, okay, how is this game going to end? And then if we go from 6, we can go to, so then Charles plays -1, okay, move 2, now we are at 6. And now if I go to 3, then I will be at -1, and Charles will be at -2. Okay, so this is a nice cycle. 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6. Right, because when I play a 6, Charles is the one making the next move. So if a player that has either a 2 or a 4 can force the other, and even a 6 actually, can force the other player, if they have the same number of points, they can force the other player into a cycle where they lose, right? Especially if I'm at a 4, I lose 1, they lose 1, I gain 1, and then they lose 1, and then I'm again at a 4. So in sum, I won't lose a point, and they will lose 1, and they will lose 1. They'll lose 2 points every turn. Whereas I will not lose a single point if I'm not mistaken. I lose 1, lose 1. Yeah, that sounds about right. So now we can talk about positions in which in which the first player would have the winning strategy, and positions in which the second player would have the winning strategy. So the numbers, if we're at numbers, the player who plays at 2, 4, 6 wins. So this is really, if we think about first player, second player, if you think about like what is a winning strategy, a winning strategy would be able to get into one of these cycles which kills the other player. So here for us we have, like, we definitely know that a winning position is if we are at a playing on a 2, on a 4, or on a 6, and it's a losing position, like we're going to lose if we are at 3 or 5 as our move, as the first player, which means for 3 and 5, Chares is the one that wins, the second player, whereas for 2, 4, 6, the second player loses. Okay, so now we know that for 3 and 5, the player loses, and now is a good time to actually think about how do you know you're going to win. Pause for 2 minutes, ask yourself that. And you have to really know you're going to win if you can get from a number that's, if you can get from n to a number that's losing, then you can definitely win. Like if I can get, so 3k and 5k are both winning. Because if I'm on 3k, I just go, if I'm on 3k, I just go, I get myself a point, and now the second player is at 3, they have to play at 4, and now I'm winning. Now I'm like going to destroy them, right? Assuming, of course, like we have to be very careful here because we're assuming we're having the same number of points at the beginning. So assuming that we have the same number of points, being on 3k is winning. Because then we'll just get into the cycling, win. And being on 5k is also winning for any k. And here's where I invite you to pause for another 5 to 10 minutes and see if you can push the problem further. I'll clear up the board now. And what we get after some plays, we get new numbers. We get, so for 7, we see we're forced to go to 8, which then 2 or 4 are both winning, which we don't want. If we can only go to a winning number, we're losing. So we go to 9, it's also, and we're looking what is 9, because we can go to 3, 9 is winning. So because all of these are winning, that makes 8 losing, which makes 7 winning. And now we know 7 is also a winning number, 8 is a losing one, 9 we know because it's 3k that it's winning, and that this seems to be like some way we'll be able to get some of these numbers whether they're winning or losing that we get. 10 is winning, so there's nothing else needs to be done, it's 5k. 11 we go to 12, we don't know what 12 is, but 12 goes to 3, which is losing. So that means 12 is winning, which means 11 is losing again. Okay, so now we have 3, 5, we have a 7 there. And I think what's also interesting to note here is prime numbers that we have that are going to be losing versus winning. Because if you have a prime number that is, right, as a player that's playing, you want to go to a losing prime, right? This is why 3k is winning. So if a prime is losing, then any multiple of that prime is going to be winning. So now there's one of two things that's possible. Either many primes are going to be losing, in which case we're going to have that every composite number, maybe starting from sum, is going to be winning. Because also now if we have a 2, we have a 7 here, it's not quite clear where the wind will blow, but it's also interesting that we'll need to look at primes at some point. Now if we go to look at 13, goes to 14, 2 and 7 are winning. We want to see if we can avoid that and actually win. We go to 15, and 15 is a 3k. So this is winning, losing, and then 13 is winning again. What is happening here is like a question that we should ask ourselves. Like, 16, what do we have with, actually, let's start with 15 is going to be winning. Now 16 goes to what? 16 can either go to 2, 4, both win, or 8, but because it can go to 8, and 8 is a losing number, that means 16 is a winning number. Some interesting thing there. Now what about 17? 17, well, we can only go to 18, and then from 18 it's of the form 3k. And actually now all the primes, if p is of the form 3k plus 2, then we know that this can only go to 3k plus 3, which is what? It's a winning number. So that means every prime of this form is losing. And also every prime of the form 5k plus 4 is also losing, given this. And every prime form 11k plus 10 is losing, and you get the picture. So now let's see what happens if a prime p is actually winning. Like, what does that even look like? If a prime p is winning, it must be able to form 3k plus 1. And then from here we go to 3k plus 2. Okay. Is there anything else we can say about this number and the information we have just now? Well, for me, no, so I'm going to keep on playing. And this is a strategy I want you to get comfortable with. Playing with a lot of numbers. Here, like we're at number, 17 now? I mean, we're looking at 18, seeing what happens. I mean, 18 is because, Because 3 is losing, 18 is winning, and ergo 17 is losing. And actually, wait a second. Yeah, that is exactly what it is. That is exactly every prime of the form p of form 3k plus 2 is actually that should be over here. P of form 3k plus 2. But we're playing with a lot of numbers here. Like, we're not stopping at 17. I still don't have the idea what I should be doing. Here's a prime of the form 3k plus 1, 19. Oh, but it's 5k plus 4. So this is also 5k plus 4, prime of that form as well. Then we go to, well, we know 20 is going to be winning, 21 is winning at 3k, 22 is 2 times, so 22, we don't know what it is, it's going to go, 2 is winning, so we don't care about that. 11, okay, that's a prime that's losing, so 22 is winning. Interesting stuff happening here. I think we might get a lot of primes that are losing just by virtue of this thing that's happening. Say 23, it's neither 3k, it's 3k plus 2, so it's in here. What about 24? 24 can go to 2, a number that's winning, so we don't care about that. Can go to 3, a number that's, so it's winning as well. 25 might be interesting, or not, because it's 5 times something, so it's not that cool. Now let's see 20. Let me actually clear up the board and continue playing, which is what I want to get you to do here. Play until you get the idea. I still don't have an idea for how I'm going to do this, so what do? I play. And what I get when I play some more is I see, okay, I mean, it's looking like every single prime that's, bigger than 13 ends up being losing. Whatever I get 29, 30. It gets me down to 3 or 5, which are losing. So I know this one's winning, so this one's losing. And it seems as though, wait, if I go to P, I'll go to P plus 1, and I need P plus 1 is losing, then, like, if this P plus 1 was losing, i.e. if P was winning, then we would have that 5, 8, 11, all these numbers cannot divide P plus 1. And if we're thinking about this inductively, only 7, 13, and 2 squared could divide it. So maybe let's even just look at, is 7 times 7 times 13, what is that? That is 91. Okay, it goes to 92, or it's because 7 and 13 are winning. So the only chance it has to not be losing it is it goes to 92. But that goes to 23, we know 23 is losing, so this one's winning. So 91 is losing. And, okay, so now what do we know? Well, we know that P plus 1 cannot be 7 times 3. Can't be divisible by 7 times 3. So it's either by 7 times 13. So it's either divisible by 7 or 13, but not both. And that also constrains it, right? That means P plus 1 can be at most 13 times 4, which is 52, right? So just by virtue of having 91 being losing, we now know that we can do this maybe inductively starting at this point. I mean, maybe let's go like 47, and then the next prime is 53. We know it goes to 54. Otherwise, it has to go to 54. And then from here, it goes to 8, which we know is what? Is losing. so this one's winning, so this one's losing. In other words, we have all the primes that are bigger than 13. We prove inductively that they are in fact losing. So now we have that every multiple of those primes is going to be winning. So now what do we have to check? Well, we have to check multiples of 7, 13, and what's it called? 8. Actually, not 8, but 4. 2 and 4. And we check 26. If we weren't immediately losing, we'd need to go to 27. But that goes to 3, so 27 is winning, which means 26 needs to be losing, so you get a 26 here. 8 2 times 13. And then every multiple of 2 times 13 is also going to be winning, because it can go to 26. And we also check 14. And 14 means either goes to 15 or immediately loses. And 15 goes to 5, which means 15 is winning, which means 14 is also losing. And those are next composite numbers. What else do we have? Well, we have to go 169 we need to check. It either goes to 13 immediately or loses. And if it goes to 170, this goes to 17, which is losing, so 170 is winning. So 169 is losing. And we also have 49. It either goes to 7 and loses immediately, or goes to 50, which, because it goes to 5, is winning, which means then 50 is winning, so 49 is losing. So we have 49 here among the composites, and that just about covers it, because now every other multiple, so now if we have a number n that's, say, bigger than all of these, or different than all of these numbers that are written on the board, then what are we going to have? And if it's divisible by any of these primes, it is immediately winning. If it's not divisible by any of these primes, then it's only divisible by 2, 7, and 13. But if n is Rodian numbers that are only divisible by these numbers, by these primes, then what do we have? We can do this on a case-by-case basis, which means if, say, 2 squared divides n, then we can say if 7 also divides n, we're going to be screwed because of this. If 13 also divides n, we're going to be messed up because of this thing right here. So 2 squared can't divide it. What if 7 divides it? Well, then 13 can. Like, we can just, do a case-by-case basis to get to every single one of these numbers. And this really just shows that the second player will win if we're on any one of these numbers. Now, what we do need to check, just to be extra careful, is that we're not going to, when you begin on one of these numbers, that you're not going to lose a lot of points, right? So we're saying these are winning, which means that now we just need double check that we haven't lost too many points in any single one of these things. So we're saying really a prime number that's not 7, 13, or 2 is going to be losing. And if we start off on a prime of that sort, then the first player first loses a point because they need to go to p plus 1. And then what we are doing is we are going on a divisor of p plus 1, so we are gaining a point. And from that divisor, we can sort of think inductively, if we had the same points, we would win, and then we are winning. So that doesn't seem like it was going to cause us any trouble. Now, what about all of these numbers? So 14, we can literally just do them actually by hand. Now that I think about it, we won't lose anywhere close to 1,000 points just to get to that cycle. We won't lose actually 500 points to get to that cycle. That's what matters for us. Maybe even maybe 250. We won't even lose 250 points to get to the cycle of 3, 4, 5, 6, 2, 3, 4, 5, 6. I believe that was the cycle. Yeah. And with that, the second player can only win with these numbers on the board, if you're starting, so if it's a prime number that is different from 7, 3, 2, or a composite number that is 8, 26, 14, 49, 91, and 169. And this is why I wanted you to, if you're getting somewhat more comfortable with combinatorics, you did some technique problems and you want to do a problem where you don't know what theory it is, I think this was a cool problem for you because it's literally just play, right? I mean, it's a game, so it's playful, but the way you solve it is just, playing around with this, trying what happens with this number, which one's winning, which one's losing. Like, in which case will I be able to get the second player to a cycle that is going to mess them up? And because we both have 1,000 points to begin with, I'm going to be pretty safe, to start as the second player to get us to a cycle. And because also the primes are where I shine, right? And when the first player is at a prime, what happens to me is I am going to gain a point, they're going to lose a point. And that's also a thing we should mention in our proof to say, okay, like anytime you're at a prime, when you play after the prime, you're going to do move 1, right? And that just solidifies your victory. I hope you enjoyed this problem, and as always, thanks for problem solving.